Good morning, everybody. Let's begin. Let's see by a show of hands how many of you can hear me well. Good. Very good. You can go ahead and lower your hand. Okay. Let's begin from where we left off. Rather quickly, let's review what we did in the last class. Well, we continued looking at different analysis techniques, right? So we started off with Kirchhoff's laws in the last class. Okay, there are two laws, Kirchhoff's current law and Kirchhoff's voltage law. Okay, any given circuit has branches. So when you're looking at branches, branch currents is what matter. When you're looking at nodes, node voltages, nodes have voltages. Okay, so the first law, Kirchhoff's first law is about currents. Kirchhoff's current law says that the sum of currents at each node is zero. Okay, if you add all the currents at any particular node, that should sum to zero. Now, and as many number of nodes are there, you can set up so many equations. And then that will help us add the number of equations in solving for the number of unknowns. Okay, to solve any system of simultaneous system of linear equations, we need as many equations as there are unknowns. Okay, if there are 10 unknowns, we need 10 equations. If there are 5 unknowns, we need 5 equations. Okay, now Kirchhoff's voltage law says that if you look at any closed path, the sum of all voltages around a closed path, the sum of all voltages around a closed path, that equals zero. That's the idea of Kirchhoff's voltage law around loop. Okay, and we saw the application of this in a bunch of different examples. Then we went on to talk about dependent current sources, dependent voltage sources. Okay, for example, this guy, the current in this branch or that dependent current source is really a function of how much current is flowing between these terminals through that resistance here. So this guy is called a dependent current source. Okay, its current is really 5 times whatever value is, whatever current is flowing through that branch, through that terminals. Okay, so that's the idea of dependent current sources. And we saw different analysis techniques, different problems, 2 problems in terms of how to solve problems with dependent current sources. Okay, in the example problems, we looked at applying KVL and KCL to different equations. How do you set up KCL at different nodes? Well, the general approach, let me write the general approach at the very end here as a way to quickly summarize the process. Okay, the general approach to KCL, KVL, in order to solve any problem using KCL and KVL is, number one, the very first thing that you do is to set up directions for voltage drop and the current flow through all the terminals, okay? And name or identify unknowns. Okay, then number of nodes gives us number of KCL equations. And we judiciously, very carefully apply KVL to set up KVL equations. Okay, and then we arrive at all the unknowns. Okay, the fundamental, the very important idea is that the directions that we set up, it doesn't have to be the actual direction of the current or the voltage drop. As long as we set up a particular direction and stick to it throughout the problem, the process is self-consistent in the sense that it will give us, if the direction of the current that we picked is different from the actual flow of current, that will be indicated by a negative sign, meaning that I should really have picked minus and plus, but that's all right. A current 3 amperes flowing in one direction is the exact same equivalent of the current flowing, a negative current flowing in the opposite direction. Okay, that's the idea. So as long as we set up a particular direction and be consistent with it, the process leads us to the solution. Okay, so that's the approach that we applied to a bunch of different problems in the last class. Okay, let's move on to the next set of problems, next chapter, which is simple resistive circuits. A very easy problem. I I think we are going to be done pretty quickly today, and then I'll give you time to work on some problems on this after today's lecture. Okay, so simple resistive circuits, series and parallel combination. Okay, so questions so far, please. Questions so far. Okay, so yes.
No, sir, I just said none. Thank you.
Of course, yeah. Yeah, so we'll continue with the different techniques of circuit analysis, calculating voltages. The next technique is to calculate voltages and currents using various simplifications. The first is to identify series and parallel connections. Okay, so let's look at some definitions for series connections here. When the same current is flowing through each device, then we say the devices are in series. Okay, by the same token, when the same voltage is seen across different devices, then we say each of these devices is connected in parallel. Okay, then we are going to look at voltage division and current division techniques. Okay, voltage expressed across parts of the circuit, current splitting. When I have some current coming out of a source, how does it split between different branches? Okay, that's the idea. Okay, so let's look at resistors in series. Okay, most oftentimes, and you're familiar with this from your previous classes. Now, when you see resistances, device terminals connected end to end, okay, they're connected only at one point, okay, then the same current, the current that is coming out of the source here has nowhere to go but through this resistance and eventually through this resistance, so on and so forth. Okay, so there is only one direction for the current to flow. There's only one direction and one route the current can take. So the same current is flowing through all the elements. Okay, two elements connected to a single node. So this is one quick way to identify a series connection is two elements when they're connected at a single node, like I mentioned earlier. That's the idea of a series connection. Okay, notice that each element only connects to one neighbor. Okay, each element connects to one neighbor. The key is to identify that the same current is flowing through all the terminals, all the elements here. Okay, there is only one current that is flowing through all the elements. Okay, now if we apply KVL around this loop, okay, around loop alpha, this guy. Okay, that's loop alpha. When you're doing KVL, you always start at the lower left-hand corner and follow a clockwise path. Okay. Now, what you can do is you can see that the voltage drop, the sum of all the different voltage drops. I have 7 resistances here. Corresponding to these 7 resistances, there are 7 voltage drops. And the voltage source itself, so that's Vs. The sum of all the voltage drops, KVL states, should equal 0. Okay, then Vs, if you rearrange this, Vs should be the sum of the voltages that are dropped across over all the resistances. Then notice the important thing is the current flowing through all the resistance is the same, Is. Okay, and I can factor out Is, giving me the expression that Vs equals to Is times R equivalent, or the equivalent resistance of a bunch of resistors in series is simply the sum of their resistances. Okay, when there are a bunch of resistances in series, and this is a result that you're very familiar with. Okay, when you have a bunch of resistances in series, their equivalent resistance simply adds in series. Okay. The important point is to notice that again, the currents are all the same. And this simplification is only possible by noticing that by factoring out Is, which is common. Okay. Okay. So that's the idea of resistors in series. So for series, the equivalent resistance is the sum of all the resistances. Okay, if there are k number of resistors, then the equivalent resistance is the sum of all the resistances in series. Okay, then one quick sanity check. It's a very, very crude sanity check, but you know, a quick way to see if you're at least in the ballpark. Correct answer is not, is that if you have a bunch of resistances in series, the overall resistance, let's say each of these is the overall resistance is larger, the equivalent resistance is larger. The equivalent resistance is 15 kilo ohms. It is definitely larger than the largest of the resistances here. So when you say the equivalent resistance is 15 kilo ohms, One sanity check is this guy, is the answer that I arrived at, okay? Is that guy greater than the greatest of the resistances that I have in series? Sure enough, that is the case. Then I'm probably in the right area. Okay, that's a quick sanity check. It does not tell you that you have the right answer, but if this condition is not true, then you know for a fact that you're somewhere wrong. Okay, so let's look at resistance in parallel. Okay, you see that the resistances here are connected at 2 points. Okay, they are not connected end to end. Earlier in series resistances, each of the resistance was only connected at one point to another resistance. But here, each resistance has two connection points. Okay, so the important thing to remember here is the total current is split between different resistances. Okay, so the total current IS is the sum of all the different currents. Okay, so in other words, if you have three different currents, think of three roads going in parallel, um, three parallel roads, okay? And then the total number of cars that are flowing through all of these roads is equals to the total number of cars to begin with. Okay, that's somehow, and we'll stretch this analogy a little further when we look at the current division technique. So if I call this I1, call this I2, call this I3, okay, the total current IS is the sum of all the branch currents in the parallel resistance. Oh, of course, let me not forget this I4 here. How did I forget that? I4, okay, so plus I4. The important thing to remember is all the circuit elements, all the resistances connected in parallel, they have the same voltage across them. Okay, all elements connected a single node with common reference node. So remember that one of these can be connected as, can be thought of as a reference node. So this is a reference node. And all the resistances R1, R2, and R3 and R4 are connected with a single node. Okay, even though they appear like three different nodes, A, B, C, even though they appear like three different nodes, they're really all a single node because this element here is a 0 ohms resistance. So this is a short, so all of these nodes are equivalent to one single node. So the point that we want to remember is all the resistances emanate, all the elements emanate from a single reference node. B is the reference node. And they connect at a common node. Okay, so that's the idea of parallel connections. And in parallel connections, like I mentioned, the voltage across all the devices, all the elements is exactly the same. Voltage is always measured with respect to a common reference. So the idea is, the voltage across this guy is exactly same as the voltage across this guy, exactly same as the voltage across this guy, which is equals to Vs. Okay, Vs is the voltage that is seen across all the resistances. Now what I can do is at node A, which is the same as this guy, I can apply KCL. Okay, I can apply KCL. And I think in some sense, I showed that to you already. Okay, the current leaving are shown in these um, resistances as IR1 or I1, IR2, IR3, and IR4 respectively. So using KCL at node A, okay, we see that the current entering is equals to the current sum of the currents leaving. So that's the current entering that is equals to the sum of the currents leaving the node. Okay, and then each of these currents IR1 can be expressed from Ohm's law as the voltage across that resistance over the resistance R1. IR2 can be expressed as the voltage across that resistance over the resistance R2. IR3 is Vs over R3, and in the interest of completeness, IR4 is Vs over R4. The important point to remember is that the voltage across all the resistances is the same. Okay, now we can factor out Vs. Okay, we factor out Vs. Okay, and then arrive at the equivalent resistance. 1 over equivalent resistance is equals to the sum of the reciprocals of the resistances, or um, or here is the canonical expression. 1 over R equivalent is the summation of all the reciprocals of the different resistances. That's the equivalent resistance. Okay, so here is a quick sanity check. Let's say I have a bunch of resistors, 4, 4, 4, 4. Okay, then the equivalent resistance 1 over R equivalent is 1 over 4 plus 1 over 4 plus that guy. Okay, which is equals to 1. So the important thing to remember is the equivalent resistance 1 ohm. This is R equivalent is less than the smallest. Okay, the equivalent resistance is lower than the lowest of the resistances. Okay, if we have a bunch of resistors, then we know for a fact that the equivalent resistance is lower than the lowest resistance. Okay, so the equivalent resistance of a set of parallel resistors is always smaller than the smallest of the single resistance. Okay, so that's the idea of parallel resistances in parallel. Okay, okay. So here is a, if I have two resistors, R1 and R2, then R equivalent can be expressed as 1 over R1 plus 1 over R2, the inverse of all of that. And then which can be simplified to be the product of resistances over the sum of resistances. Okay, so when I have two resistors in parallel, the equivalent resistance is their product divided by their sum. Okay, that's resistors in parallel. Okay, so here is an example. Solve the following circuit for IS, I1, and I2. The question is, what is the value of the resistors are given, okay, and the currents through each of these is given. Well, the currents are not given. That is what we are supposed to find out. Okay, the overall voltage is given. Okay, the overall voltage is given, and we are expected to find each of the branch currents. Okay, let's see how we go about doing that. In order to solve for IS, the first step that I want to do is find the R total. Once I have R total, the total equivalent resistance, then I am going to express this whole circuit as 120 volts in series with R total. Then IS, the current flowing, will be equals to 120 volts divided by R total. Okay, so my idea is to find the total equivalent resistance. Okay, so let me start by noting that this guy, these two are in series. Okay, these two resistances, 3 ohms and 6 ohms, are in series. So I can simply add them to form a 9 ohm resistor. Okay, so that's a 9 ohm resistance. Then that 9 ohm resistance, the equivalent of that 9 ohm resistance, is in parallel to this 18 ohm resistance. Okay, so let's see. Let me redraw that here. Okay, so the first simplification is that these two are in series. So I'm going to replace them with their equivalent. So 9 ohms is the equivalent. And then this is, of course, 18 ohms. And this guy is 4 ohms. Okay, now notice that the 18 ohms is in parallel. That's the shorthand for parallel to 9 ohms. So I can do the closed form approach, product by sum, to find the equivalent resistance, which gives me 6 ohms. So now I can simplify this to be 4 ohms in series with 18 in parallel with 9 ohms, which is 6 ohms. So verify your sanity check, apply your sanity check here. The equivalent resistance of 18 in parallel to 9 is found to be 6 ohms. So the equivalent resistance, 6 ohms, is less than the lowest of the resistances here. Okay. Okay. So the R total, the equivalent resistance here of the entire network of resistors is 10 ohms. Okay, once I have 10 ohms, I should be able to find the value of IS. IS, like I mentioned, is 120 over the R total, which comes out to be 12 volts. Okay, so let's see. This is this step here. Okay, and this is this step over here. Okay, the equivalent resistance is 10 ohms, so on and so forth. Okay. Now, we found the value of IS. IS has been found to be 10 amperes. Okay. Let's see how that is splitting between I1 and I2. Okay. Let's see how that current is splitting between I1 and I2. Excuse me. So if you look at this, okay, 120 volts, the amount of current flowing here is IS. That is shown over here to be 12 amperes. Okay, that's the idea. Now, from that, I should be able to find the value of voltage V1 over here of this equivalent branch, this guy V1. Okay, There are a bunch of different ways to solve this problem, but we just choose to use this guy, okay? So in order to find V1, we see that it is I times R. So this is the current flowing, and this is the R equivalent of that branch. So that's 72 volts. So there is 72 volts across these two terminals. So in order to find the current I1 through this branch, I simply divide 72 by 18, which is a value of 4 amperes. Okay. Remember this is 10 amperes. And this guy, I1 came out to be 4 amperes. So this has to be 6 amperes. Okay. So there is more than, this is 12 amperes, isn't it? Okay. This is 12 amperes. Then 4 amperes is flowing, and the remaining 8 amperes has to flow in this branch. Okay. So all I have done is to look at the voltage drop that is across these two terminals. Okay, which is simply the current times the equivalent resistance. The current is 12 amperes, and the equivalent resistance of those two of the overall circuit here is 6 ohms. So it gave me a total of 72 ohms. So knowing that this guy is 72 volts, I should be able to find the value of the current in this resistance using Ohm's law, which is 72 volts divided by 18 ohms. Okay, so which gave me a current of 4 amperes. So that's the amount of current flowing in this 8 ohm resistance, 4 amperes. Okay, so I started with 12 amperes to begin with, out of which 4 amperes is flowing through this branch. Therefore, the remaining, which is 8 amperes, has to flow through this branch. Okay, in the next set of slides, I'll probably show you a more formal way of finding, okay, the total currents, okay, how the current is split, how the total current is split between two parallel paths. Questions so far, please? Okay. All right. So that's the idea of voltage divider and current divider circuits. Okay. Voltage division and current division circuit. So I gave you an analogy earlier that resistances in parallel can be thought of as two roads in parallel. Okay. Let's say R1 and R2. I'm talking about a simile, an analogy for current divider. Okay, so think of resistance as being similar to number of stop signs along a road. Okay, think of electrical resistance as the number of stop signs or signals. Okay, let's say R1 is much greater than R2. Okay, let's say the resistance, the number of stop signs, the number of speed bumps, and the number of signals in R1 is much greater than R2. There is a smooth flow in R2. It's a much better ride. Okay, now you're trying to send traffic across these two roads, through these two roads, I total. Which of these two roads do you think has more cars? So let's say I'm trying to send, let's say there's a total of 100 cars.
I would assume more would go to R2 because it's less resistive.
Yes, more would go to R2, and therefore, out of the 100 cars that are flowing, a big chunk, 80%, I'm just pulling numbers out of thin air, 80 cars are going through R2 because the resistance is much smaller there. Only a few cars are flowing through R1. So that's more or less the analogy that we understand. Okay, so and then I'll show you a more accurate equation to find out how much current, what ratio, what percentage of current, um, total current is flowing through R1 and what percentage is going through R2. But the idea is that if you think of resistances as being similar to uh, stop signs or signals, then it makes a bit more intuitive sense. Okay, the idea of voltage division, current division makes more sense. Okay, okay. So let's look at voltage divider first before we even talk about current division, voltage division. Okay, voltage division, a very efficient way to create two signal levels. Okay, let's say there is a total voltage source Vs, and then you want to split that into V1 and V2. One quick way, an efficient way, though not a very accurate way because resistances have a lot of tolerance associated with them. A very efficient way is to simply create two voltage levels using voltage division. Okay, so V1 plus V2 should equal Vs, right? So that's something we know for a fact from KVL. Okay, we know for a fact that V1 plus V2 should equal Vs, the total voltage. Okay, so if I have to find the total current here, if I have to find the total current IS, all I simply have to do is Vs or what is the total resistance, two resistances in series, meaning that the equivalent resistance is the sum of their resistances. So that gives me the IS. IS is Vs over R1 plus R2. Now what is V1? How do I find out V1? In order to remember, these are in series. So the same current IS is flowing through R1 and R2. So if I have to find the voltage through R1, voltage across R1, which is shown as V1, then I should simply multiply IS times R1. But I just found out that IS is Vs over R1 plus R2. That multiplied by R1 gives me the voltage across R1. Okay, so this voltage is R1 by R1 plus R2 times Vs. Okay, this voltage, by the same analogy, this voltage here would be R2 over R1 plus R2 times Vs. So the resistance R2 times the total voltage by the total resistance. Okay, that's the idea. So add them up. What do you have? R1 plus R2 over R1 plus R2 times Vs. So R1, the numerator and the denominator cancel. You're left with a Vs. You get back your Vs, which is applied. Okay. So the voltage, the idea of voltage division is that when you have two resistances like so, okay, when you have two resistances like so, the voltage drop across this resistance is R1 over R1 plus R2 times the total voltage applied Vs. And is this guy is R2 over R1 plus R2 times Vs. Okay, so that's the idea of voltage division. So what you have to remember is that this is a fraction. This is a fraction. The voltage drop, here is the intuition behind what you want to remember. The voltage dropped across R1. So this is V1, right? V2 is proportional to the resistance R1. Voltage dropped across R2, V2 is proportional to R2. Okay, so that is the idea of voltage division that you want to understand. Okay, if this resistance is large, implies a large percentage of this voltage source, of this voltage is dropped across here. Okay, if this is small, then a small percentage of that is dropped across. So the intuition is, so let me clear up all of this. Sorry about that. Okay, the intuition is V1, this guy V1 is proportional to R1. V2, the voltage drop across this resistance is proportional to the magnitude of R2. Okay, we'll see that in, so that's exactly shown here. V1 is Vs times R1 over R1 plus R2. V2 is Vs times R2 over R1 plus R2. Okay, that's the idea of voltage division. Okay, let's see. Here is an example. Even before doing the math, even without doing the math, okay, let's try to get some intuitive, let's try to predict more or less the relative values of the voltages across here. Okay, let me call this V1. Let me call this V2. Okay, so of the 100 volts that is applied here, a big percentage is going to drop across this 100 ohms here because that's big, and a small percentage is going to drop across this resistance over here because that's small. Okay, that's the prediction that we are making, directly resulting from the voltage division circuit that I saw earlier. Okay, now if you want to find out V1, if you remember, is the value Vs times R1 over R1 plus R2. In this case, Vs is 100 volts, R1 is 25 kilo ohms. This guy is 100 plus 25, which is 125 kilo ohms. Okay, then you have V1 coming out to be 20 volts. Okay, V2 is Vs times R2 over R1 plus R2, and you find that it is 80 volts. So as you can see, once I do the math, okay, my predictions are in agreement with, my predictions are pretty much in agreement with the calculated values. I found out that a small percentage, 20% of the total voltage, 100 volts, is dropped across this resistance. That's the small percentage, as opposed to this guy, 80 volts, which is dropped, a big percentage is dropped across R2. That's mainly owing to the fact that the voltage that is dropped across a big resistance is big. Okay, does that make sense? Now, So that's the idea of voltage division. If you have to find the resistance through R2, or I'm sorry, if you want to find the voltage through resistance R2, then you simply take the total applied voltage by the total applied resistance, by the total resistance seen times R2, because that is what we are trying to look at the current voltage drop across. Questions, please. Okay. A small percentage is dropped across a smaller resistance, the big percentage across a big resistance. Okay. A current will divide resistances. A current will divide between resistances in parallel. Okay. This is going back. So just like the voltage divided between two resistors in series, so voltage, let me put it right here, voltage. So voltage divides between resistors in series. Okay, voltage divides between resistors in series. Okay, so ignore the T off at the end. Voltage, dang. Voltage divides between resistors in series. Okay, now the opposite is true for currents. When you have a current flowing through a parallel resistances, that's going to divide. Okay, so the intuition is slightly different. It is inverse relationship. Okay, earlier, voltage across a resistance is proportional to its value, right? Here, it's going to be dependent on the other resistance. Okay, I'll show you what I mean in a second. Okay, a current will divide between resistances in parallel. Okay, the important thing to remember is the voltage is exactly the same for both of these resistances. Okay, if V is the voltage, then the same voltage is seen across these two resistances, this guy. Okay, resistors in parallel. So I1 R1, which is the voltage across the resistance R1, is exactly the same as I times R in the second resistance, okay? Because they are connected in parallel, their voltages are exactly the same, okay? So I1 R1 is exactly equals to I2 R2, and then we can use the equivalent resistance. The equivalent resistance is R1 times R2 by R1 plus R2. That's the R equivalent. So if there is a current that is flowing like so, an R equivalent here. Now, what is the voltage dropped V over here? Well, voltage dropped V should be equals to the total current IS times the R equivalent. Okay, so that is IS times R1 times R2 by R1 plus R2. That's the total voltage. Okay, now as you can see, that's the total voltage. This guy is Vs, okay, which is R1, R2 by R1 plus R2. That's the total equivalent resistance times Is. Okay, so that's exactly what I found here. Now we should be able to solve for I1. I1 is Vs over R1. That's exactly what is done here. I1 is Vs over R1. So this guy over R1. So you're left with I1 is R2 over R1 plus R2 times Is. Okay, so I2 is R1 over R1 plus R2 over Is. Okay, you see the difference between voltage division and current division here. I1 is proportional to R2. I2 is proportional to R1. Okay, if R2 is large, then I1 will be large. If R1 is small, then I2 will be small. And I'll show you using an example here, hopefully. But the idea is that is exactly the opposite relationship to voltage division. Okay, voltage V1 was proportional to R1, V2 was proportional to R2, if you remember. Okay, V1 proportional to R1, V2 proportional to R2. But the idea in current division is that the total current, the current split is proportional to the other resistance. Okay, and that can be thought of using, I better show that using an example here. Okay, here, find the current through the 4 ohm resistance here. Okay, the question is, what is the current that is flowing here? Okay, find the current in the 4 ohm resistance. Okay, there are many ways to approach the problem. We are following using current division here. So we'll see how to find the idea of the current I through 4 ohm resistance. So let's notice that this current is 10 amperes. Okay, so 10 amperes current source. RP on the right hand side is 1.6 in series with 4 in parallel with 6. So the first thing is, remember that these two resistances, 4 ohms, are in parallel with 6 ohms. So the equivalent resistance is 4 times 6 by 4 plus 6. Okay, so that's the idea, which is 2.4. So I have 1.6 in series with 2.4, which comes out to be 4 ohms. Okay, so that's the idea. The key is to notice that 4 ohms and 6 ohms are in parallel. Okay, now then the equivalent resistance will be 16 ohms in series or in parallel with another 4 ohms. Okay. Okay, let me redraw this. Okay. There is a total of 10 amperes here. Okay. That is in parallel with 16 ohms, which is in parallel with 4 ohms. Okay, that 4 ohms is different from this 4 ohms. That's the total equivalent of all of these resistances, which is different from that single 4 ohm resistance itself. But the important thing that we want to understand is, out of the 10 amperes here, the amount of current flowing through this is proportional to this resistance 4 ohms here. Okay, so if you look at the current RP on the right hand side, okay, That's RP. If you think of that as RP, which is divided into these two branch currents. So this RP is the current through this IRP. Okay, the current through this IRP or IP is, if you're trying to find the current through this resistance, you have to do 16, the other resistance, over 16 plus 4 times 10. Okay, what you get is 8 amperes. Okay, oops. So the idea is there is a the idea is 8 amperes of current is flowing through this, and 2 amperes of current is flowing through this branch. How did I get that? Simple voltage division. In order to find IP, which is this guy, okay, IP, remember, current is divided in R2 over R1 plus R2 times 10 amperes. Let me go back here. So current in I1 is proportional to the other resistance. Current in I2 is proportional to R1. Okay, so that's exactly what I do. I2 is R1 over R1 plus R2. Okay, if you want to find the current in one resistance, multiply IS by R2 over the sum. Okay, you have to, the numerator will be the other resistance. That's what you have to remember. Okay, that's exactly what I'm doing here. So the my goal is to find the current through this resistance, 4 ohm resistance here. So I multiply 10 amperes by the other value, 16 ohms, by the sum, 16 plus 4. So which comes out to be 8 amperes. Okay, the idea of current division. Okay, in order to find, so the idea is that 4 amperes of 8 amperes of current. So that gives me 8 amperes. So that 8 amperes is shown here, 8 amperes of current. And how is that split between these two branches? So in order to find this current through 4 ohms, what I do is I take the 8 amperes current that is coming in and divide it in this ratio. 6 ohms by 6 plus 4 is flowing through this, I 4 ohms. I 6 ohms, current through 6 ohms is going to be 4 ohms by 6 ohms plus 4 ohms into 8 amperes. Okay, so that's the idea of current division. Okay, if I have to find the current through one resistance, then use the opposite resistance, okay, times this 8 amperes by the sum of those two resistances. Okay, that's exactly what I'm doing here. Okay, so the idea is that 48 by 10, 4.8 is going through this resistance. Okay, sure enough, I have 4.8 amperes flowing through the 4 ohm resistance. Okay, so that's the idea of current division. Current division is that questions, please? Questions so far? Okay, let me go back and quickly review what I have done here. I found the first of all, in order to find, okay, in order to find, so the question is to find the current through this resistance. So let me eliminate all the annotations here. The question is to find the total current in this resistance. Okay, so the first thing I do is look at the total current here. Okay, look at the total current, and I'm going to make a simplification here. This guy. What if there are three resistances in parallel from Jonathan, as in this guy? Or if there are three resistances in parallel? If there are three resistances in parallel, then what happens is, let's say if I can add a page here. Okay, I total is splitting between R1, R2, and R3. Okay, I total is splitting between R1, R2, and R3. The total equivalent resistance, R equivalent, is 1 over R1 plus 1 over R2 plus 1 over R3, the whole inverse. So R equivalent will come out to be R1, R2, R3 times R1, R2 plus R2, R3 plus R1, R3. Okay. Whole inverse, or R equivalent will come out to be R1, R2, R3. Why? R1, R2 plus R2, R3 plus R1, R3. Okay, now if I have to find the current through this guy, that will be, let me call this I1. So I1 will be the total voltage V time V divided by, so I1, if I have to find, it'll be V divided by R1. Okay, so it'll be R equivalent is that guy. So the total voltage V is I total times the R equivalent, R1, R2, R3 by that guy, R1, R2 plus R2, R3 plus R1, R3. Okay, that is total V. Now, if I have to find I1 will be V1 over R1, or V over, I'm sorry, I1 is V over R1, right? This guy. So here comes your result. If you do this, it's going to come out to R2, R3 times IT by R1, R2 plus R2, R3 plus R3, R1. So I2 can be written as, if there are three resistances in parallel, then I2 will be R1 times R3 times IT over R1, R2, R2, R3 plus R3, R1. Similarly, I3 will be R1, R2, I total by the same idea, R1, R2 plus R2, R3 plus R1, R. Does that make sense, Jonathan? So the idea is, if there is more than one resistances, the current through I2 does not see the resistance R2 in its equation. Okay, so thank you. It's a very good question. So going back, in order to find the resistance through, so the first thing is in this 10 amperes current, this 10 amperes current, was the 10 amperes, is splitting between 16 ohms and the R equivalent. So in order to find the current through R equivalent, what I do is 10 amperes is split between 16 and R equivalent. Using current division, I can apply 16. I'm trying to find the current through R equivalent. So that will be the opposite, the other resistance, 16 over 16 plus 4. Okay, which comes out to be 8 amperes. So I just found out that the current here is 8 amperes. And the current here, by analogy, is 2 amperes. Okay, so this current is 8 amperes. So I first used voltage division, current division at that node. Okay, then I apply current division at this node to split this 8 ampere current between 4 ohms and 6 ohms. Okay, that's exactly what is being done here. This 8 amperes is divided, this 8 amperes is divided between 4 ohms and 6 ohms. Okay, so if you have to find the current through 4 ohm resistance, you use the other resistance, which is 6 ohms. Okay, other questions, please. Okay, so that's the idea of voltage division. And that kind of concludes our, let's see where we are in terms of, so hopefully if we are on schedule or ahead of schedule, we'll get a chance to work on some problems in the coming class. So 6.1 and 6.2, we are, our goal is to have completed resistances in series and parallel, voltage and current division circuits. So we are pretty much, as a matter of fact, we are ahead of schedule. So probably we can stop here, and what we will do is we'll come back. Okay, we'll come back and work on some problems and see if we can move further along. Okay, questions, please.